In chapter 6, we're going to meet three specific kinds of forces to sort of add into our toolbox of things that we know about. In order, these are going to be the force of friction, illustrated here by the force of friction heating up the phosphor at the top of the match, and so the match ignites. And we're going to learn about the two types of friction that can exist. We're also going to learn about air drag, so how jumping through the air with one of these jumpsuits can be fun and not fatal. Basically, after we have a sense of what terminal speed is, we have a good idea for why their suits are shaped the way that they are. And then the third that we're going to talk about is not a physical cause of a force, but a force that we see causing motion, in particular, motion around in a circle. So you have a motorcycle and a go-kart able to drive around inside of this hoop in a way that looks rather peculiar compared to the way the other people are oriented. And this is possible because they are in circular motion, and the normal force that's pushing on them from the wall is pointed in towards the center of the circle, so it continually changes the direction of their motion into a circle. And then that normal force can be quite large if they're going fast enough. And then going along with that force, normal force from the wall onto the motorcycle or onto the go-kart is going to be a force of static friction that can point up the wall. So if they're going around fast enough, they can do these gravity-defying things, like drive horizontally. All right, so that's our goal. Meet these three categories of forces: very general force of friction, air drag, and then centripetal force. The first of those is going to be friction. Whenever I have two objects in contact with one another, those objects, like say my two hands, are not able to pass through one another because each exerts a normal force on the other. Okay, so that's what makes solid forces solid. I can rest my coffee cup on my desk, and the coffee cup doesn't go through my desk because there's a normal force that the desk exerts on my coffee cup. So normal force prevents two solid objects from occupying the same space. That is the contact force that's perpendicular to the interface. Could also have a force that is parallel to the interface between two objects, and that is friction. Okay. If the two objects in contact are not moving relative to one another, then what we have is static friction, which I'll talk about in just a second. Now, the wording is very important here. Does not say that those two objects are overall not moving. It's just the two objects in contact are not moving relative to each other. Okay. If you set a toolbox in the bed of a pickup truck and drive down the road, what keeps the toolbox moving along with the truck? Static friction. If static friction fails, then that toolbox is going to start to slide. Okay. So we can have static friction with an object that's moving. The point is, it's static friction if the two objects in contact are not moving relative to one another. All right. So with static friction, we need to be careful. There's not a general equation for how big the force of static friction is, just as a general statement. What we do know is that the magnitude of the force of static friction can be no larger than this maximum value. So we have a coefficient of static friction, your book's notation, that is a mu with a subscript s. So that's a dimensionless coefficient of static friction. And the maximum force of static friction, the maximum magnitude it can take, is also proportional to the normal force. So the larger the normal force, the larger this maximum value that static friction can take. As an example, I have a block. It has weight, so that's directed down, and it's being pushed down and to the left. So the normal force on this block is going to be large enough to cancel out the weight of the block, plus cancel out this vertical component of the force that's pushing down. That would give us the normal force. And then we could go off and calculate, if I know what this interface is between this object, the block, and the floor, that tells us what the coefficient of static friction is. And then we'll find the largest value that static friction can take. Okay. So if the force I need to hold this object in equilibrium is less than that maximum, then the object remains in equilibrium. And I can find the direction and magnitude of the force of static friction by finding how big this force has to be, in this example, to cancel out the horizontal component of this force that I'm pushing on the block with. Okay. And as long as that doesn't exceed the maximum, then we're all good, and this block would remain in place. Static friction would hold. And so the force of static friction is sort of like the way we deal with a normal force. There's not necessarily going to be a direct equation. We can find what the maximum value is, but the force of static friction can take any value up to that maximum. What we do know is that the force of static friction is going to try to have an object remain in equilibrium. So find the net force resulting from everything except static friction, see which way that net force is pointing. So in this example, it would be a net force of pointing to the left out of the push, and then static friction is going to point to the right to cancel that out. All right, so my little Blues Brothers Kokomo, Indiana reference there. The other kind of friction, the Western and the country in Western, is kinetic friction. So again, it is a contact force that's parallel to the interface between two objects in contact, but it is kinetic friction when there's relative motion at the interface. Empirically, we have a simple relationship for how strong the force of kinetic friction is. It's, again, a dimensionless coefficient, mu sub k, times the normal force. And the force of kinetic friction is going to point opposite to the direction of motion of the object. So kinetic friction tries to oppose the motion. So if the velocity is pointing in a particular direction, the force of kinetic friction on that same object will point in the opposite direction as the velocity. All right. For most materials, we find that the coefficient of kinetic friction is less than the coefficient of static friction. So a place in your life where this might have come up. So you're trying to move furniture and you have like a heavy filing cabinet or something fairly heavy. You will have observed that you have to push harder to get it to move to begin with than to keep it moving once it's moving. And that's a reflection that generally friction is going to be a weaker force once you already are in relative motion. So one object is sliding over the other. Than when the two objects are at rest. And at the atomic scale, you're essentially getting attractive bonds across from one object to the other, holding it in place. All right. An exception to that is Teflon. Teflon famously is just as slippery if you're moving as if you're not moving. But for most material interfaces, the coefficient of kinetic friction is smaller than the coefficient of static friction. All right, let's try some questions. So I have 3 pine blocks, each with an identical mass, so 1, 2, and 3, are sitting on a rough surface as shown. If the same horizontal force is applied to each block, which one of the following statements is false? So 4 of these are true, 1 is false. So think about what you think the answer is. Check it over with your physics friend, and then we'll go over the answer together. All right. So B is the one that's false. But let's go through them all. The coefficient of kinetic friction is the same for all 3 blocks. Yes, that's true, because it is pine for each of the blocks, and it's the same rough surface for the object that they're on. So same material gives you the same coefficient of kinetic friction. The magnitude of force of kinetic friction is greater for block 3. Well, so we just said that the coefficient is the same, and the blocks all have the same mass, therefore they have the same weight, therefore they have to have the same normal force. None of these blocks is shooting up into the air, and none of these blocks is sinking through this horizontal surface. So they all have the same normal force, same coefficient of kinetic friction, same normal force. They all have the same force of kinetic friction. Right. C, the normal force exerted by the surface is the same for all 3 blocks. Correct, because it's big enough to cancel out the weight of the box. D, block 3 has the greatest apparent area in contact with the surface. Sort of as drawn. Yes, agreed. That does not matter. And this is a fun, subtle point from the science of tribology, which is the science of friction. You might want to think that since there is a greater surface area for block 3 than, say, block 2, there would be a greater force of kinetic friction. But that greater surface area is offset by the normal force being spread out over that larger surface area. And so it's like a pressure force. Okay. And those two, both being like a larger area in contact, giving you more, atomic scale bonds, it's precisely canceled out by the fact that the weight of that block is spread out over a larger area. The pressure that that block exerts is smaller. So those two things cancel out, meaning that all of these 1, 2, and 3 have the same force of friction on them, same force of kinetic friction, regardless of their surface area in contact. Or if I take object 2 and put it in different orientations on the block, on the horizontal surface, I would have the same kinetic friction force. All right. Option E, if the horizontal force is the minimum to start block 1 moving, then that same force should be used to start block 2 or block 3 moving. That's true. So it'd have the same amount of static friction to overcome to send any of these blocks into motion, because the maximum force of static friction is coefficient of static friction, which is the same for each, times the normal force, which is the same for each. All right, let's try another one. This one's a little quick computation. On a rainy evening, a truck is driving along a straight, level road at 25 meters per second. So that's about 50 miles per hour. The driver panics when a deer runs onto the road and locks the wheels while braking. So the wheels are no longer turning, and the truck is going to just skid. All right. If the coefficient of friction for the wheel road interface is 0.68, how far does a truck slide before it stops? It's a great way to use your kinematics that we fought so hard to learn. All right, so go through, try to calculate that. And then let's see what the answer is. All right, so it is 47 meters, and let's talk about where that's coming from. I have V, so from the kinematics equation that does not involve time, V final squared minus V initial squared, ooh, that's a rough 2, equals twice the acceleration times the displacement. And we are trying to calculate the displacement. Now, the acceleration is coming from the force of kinetic friction that's opposing the motion. And that well, so let's just write out the force of kinetic friction first, and we'll go from there. F sub k is going to equal the normal force, which offsets the weight, times the coefficient of kinetic friction, U sub k. Okay. That is the only force acting in the horizontal direction. So Newton's second law of motion, I sum up all the forces. That's only one. We have mass times acceleration is going to equal coefficient of kinetic friction times the normal force, which is going to be mg. And so then the mass of the truck cancels out. And the acceleration is the coefficient of kinetic friction times g. So we plug that into there. And the truck ends at rest. So v final squared is 0. And we can solve for the displacement. Okay. And you put in numbers, that is 47 meters. That's how far it has to slide. Important to know that your stopping distance goes as your speed squared. That's a good thing to know in life. Don't tailgate. If you're going at a high rate of speed, you're going to have a super duper acceleration to slow down enough in a short period of time or equivalently in a short distance. And you can only get so much. Friction can only be so strong. And get this cleaned up. And then we'll go to the next slide and we have another question on friction. All right, this is a cute problem. Or I think it's cute. There's a 1 kilogram block is placed against a wall and is held stationary by a force of 8 newtons applied at 45 degrees. So I've got some force F here. What is the magnitude of the friction force? So see if you can calculate this as a case of an equilibrium object. So this block is held in equilibrium. What is the force of friction that's going to allow it to be in equilibrium? So try to calculate that. Right, and it is 4.1 newtons, and let's try to see why. Free body diagram from the center of mass of that block. So not drawn great, but hopefully you can be forgiving. It's a force of gravity acting down. Part of this force is pushing the block into the wall, and part of your 8 Newton force is actually pushing it up the wall. There is a normal force coming from the wall onto the block to cancel out your part of your push that's trying to push it through the wall. So we think about this in like components of forces along X and Y directions. What do we have? I'm going to have the normal force. It's going to cancel out this part of the push. And then out of forces that have just vertical components, I have part of my push going up. I have a stronger force of gravity going down. So that tells me that the force of static friction has to go up. And then those 3 forces have to cancel each other out when I add them together. So I'm going to mark them off with 1 bar. Okay. So writing that out in Newton's third law, or Newton's first law of motion, force of static friction up plus your push, and it's 45-degree right triangle. So that's your push over root 2 minus the weight equals 0. So Newton's first law of motion along the y direction, I've got those three forces. We put values in, move the weight, and you're part of the push that's directed up the wall to the other side. You come up with a force of static friction of 4.1 newtons. All right.